Hi everyone, thanks for tuning back in. In this specific video, we're going to talk about operational availability. In a previous video, we reviewed the 4 types of availability that you could monitor on a BESS to calculate kind of its performance, equipment availability, operational availability, power availability, and then energy availability. In the previous video, we reviewed in detail the equipment availability, where you can monitor if the equipment is on or off. We've also kind of identified that there is blind spot in this methodology. Your equipment can be on, but not being able to deliver power. So if you have an highly imbalanced system or D rates, so you might not capture that. The second type of availability that you can then layer on top of it is operational availability. And that's what we're going to review in this video. Operational availability is measuring how well you're meeting your set points. So the granularity is pretty high. By granularity, we mean how much resolution can you measure this with. This is going to be measured in megawatts, so it's very granular. The coverage is, can you measure that in every interval of production, of operation, so like 24 hours a day, 7 days a week, all the time, or just in specific time window. In the case of operational availability, you can only assess that when you actually have a set point and are dispatching the asset. So it's very low. On a 4-hour battery, it might be just like for 9-10 hours a day. On a 2-hour battery, only like 5 hours a day as you're charging and discharging if you're doing 1 cycle per day. The accuracy is pretty high. We're comparing a set point to a metered value, so it's very accurate, but there's still a bunch of blind spots. The biggest blind spot is like if your set point is less than the nameplate power, your contractual megawatt, like the kind of maximum you can deliver, then you don't know above that. So if you have a 100 megawatt plant and there's some unavailability and you dispatch only 50 megawatt and get 50 megawatt, here we're going to assess that it's 100% available. It's able to deliver the 50 megawatts. You don't really know above that what it could deliver. This is going to be all measured in megawatts, and we'll convert this into percent of contracted power. So the example we're going to use to discuss how we measure operational availability is state of charge imbalance. Let's say, like, take a very extreme case. Let's say you have 10 inverter stations. Half of them are empty. There's no more energy in the batteries. The other half have still 20%. The overall BESS might report 10% of energy availability. It might report like 20 megawatt hour remaining, but half of the station cannot deliver any power. So you're going to be limited in power to 50% of your expected total power. So maybe the energy representation is accurate, but you cannot deliver the power. So in most cases, that's a problem. You're expecting your BESS to be able to deliver that energy at its nameplate power. And that's present in every system to a certain level at the end of charge and the end of discharge. So here you can see we have a BESS that we've been dispatching at 100% of its power. And before we reach 0% state of charge, the green line, we start to see a power taper. But power taper, we mean like we cannot maintain that set point anymore, and then we're starting to lose power at the point of interconnection. That's your POI. This is caused by the individual PCSs dropping off, getting fully discharged, one after the other, not all at the same time. And in this case, like you could imagine, there's maybe one that was quite imbalanced, and it's actually running for much longer. All this can be managed to an extent by your power plant controller by dispatching all these PCSs at different power level to try to get them to all finish charge at the same time. But in all cases, there's always some taper at the end, and the amount of it is kind of unknown and will vary depending on your system kind of balance. This is a representation of the same thing, but with real data. And you can see that at some point here, we started to see a taper. And here you see it's kind of gradual because this system has 54 PCSs. So every PCS that drops off is like 2% loss. So you're going to see the first one kind of dropped off here. And then you got a bunch that dropped off after this. And then more here. And then at some point, and this is pretty typical in most system is at some point we were still maintaining our set point here. At some point, the system realized that it could not maintain power and lower its set point. And then we started to follow. We were able to meet the set point. And at some point here, we were still not empty. At this point here, there's still 0.6% SOC. Maybe here there was still like 1%. There's an attempt to try to discharge a bit more, and then you could see that at this point, like the red line is what we could deliver. We're not able to deliver that. So it means like the actual available power at that time was like the red line here. The behavior of the dispatch, the set point, will highly depend on who controls the BESS, their control algorithm. You don't really know how this is going to behave. And so we could measure, I don't know if I have another example here. Like here, we could measure all the shortfall, but when we got into this area here, we could not really, there was no more shortfall to measure because the set point was getting lowered. So when we talked about line spots and then the coverage, well, we only were able to assess it here, not here. And then here we were able to assess it again because we actually increased our set points. So there's only these two locations where we were able to assess the underperformance. This is very useful for performance engineering. It gives you a sense of the imbalance and kind of why this is happening, and also gives you a sense of how the plant is getting dispatched. This can indicate like telemetry problem where you're still dispatching here that you have 0.6% set of charge, but really like there's almost no power left to dispatch. Really, you should have probably told the system at this point that it was at 0%. With this information, you can monitor the state of balance. This is a imbalance kind of example. At the end of charge or the end of discharge will look the same. There's other type of potential kind of derate that this would catch. So to evaluate this, you're gonna have to do a two-step process. First, you need to measure the shortfall, meaning like kind of that distance here between your set point and your actual value. You're going to do, for the purpose of availability, we're going to do set point minus actual, and then of the absolute values, and when we'll only measure if it's under delivering, meaning like if we were over delivering, we're going to ignore that. If you over delivering, you're going to assume that the system is quite available since it's over delivering. That'd be more like an accuracy kind of control, power control accuracy problem. We're going to use a deadband we need some tolerance, like power measurements are not perfectly accurate. The ability to maintain a set point, you're never going to be 100% accurate. So you want your algorithm here to be able to account for a tolerance. You can see it here. That's that green line here is the tolerance. So as long as you're in this tolerance, you're not going to trigger a shortfall kind of event. So here you can see like this zone here represent this peak here. And then this zone here is represented by this peak. Another thing that you might want to account for is ramp rate. And that'll be based on the performance of your system and its maybe ramp rate settings. If you know your system is designed to ramp slowly and then there was a very fast ramp rate signal, you might want to ignore, or we're not really ignoring, but you might want to increase your tolerance band for those instances. So in this case here, there's a sharp drop here that's kind of maybe a bit beyond what typically is expected of the system. So we're going to increase the tolerance band for that spot. This can be useful when you're ramping up or down. And this can be adjusted. It will be really project dependent. So you're going to adjust your kind of dead band and then measure your shortfall. And then from these numbers, we're going to then, if there is a shortfall, we outside of the dead band, then we're going to have to process what is then the availability of the plant. The idea is like if you're asking for 100 megawatt, only getting 90 megawatts, the availability of the BESS is really 90 megawatt. If you're asking for 70 and only getting 30, the availability of the BESS is just 30. It's whatever you're delivering. So for every interval, we're going to do this every minute, every 5 minutes, whatever data you have. If the shortfall is exceeded the dead band, and you're within the SOC limit. So let's say you're not fully charged or not fully discharged. So you're within where you were expecting to be able to operate. You're going to use the actual delivery value as your availability number in megawatts. Now, this is going to be directional. If you're at the top, you're fully charged, and you're asking it to charge again, we're going to ignore that. And then similarly at the bottom, if you fully discharge and then you're asking to discharge more, then you're going to assume it's available. This condition should not happen, but shall your system send self-discharge set points when you're reporting 0? We would ignore this. So in order to compute this type of things, you would likely use what's called a Jupyter notebook. So this is a Jupyter notebook. It's actually a Marimo notebook. You would have a step where you pull your data. So this is a comprehensive kind of notebook that actually process all the different availability from your equipment, your power, pull information about the site. We're just going to look at the step that computes the operational availability, but you would have your docs, markdown files, your settings, and then you would pull the data. You only need set points, actual, and state of charge for this. These are 1 minute timestamps, and this is the same data we looked into in the presentation. Then you could have lots of charts that shows the different steps. So you could quality control, and you put that in the report. This can get emailed every day. So here you can see when we started to derate here, our state of charge was still 6%. So for sure at 6%, we would still expect to be able to run at full power. After about exactly 15 minutes, I think a bit less, the system realized that it was not maintaining set points, started to ramp down. There's a bit of discrepancy here. So as we process the delta, at some point here, there's a 30 megawatt short. This is the ramp that we monitor, the ramp rate, and we adjust the deadband. Really, actually, at this stage where we were not maintaining, the set point was steady, so there was no ramping. So all this is kind of going to be considered like unavailable, and then we're going to use the actual value at the time. I mean, here we were on the 108 instead of 150. So we're going to use those values here, 120, as the available megawatt for the site. The site was not able to deliver more than that. As the set points lowered, the available power went back to 150 megawatts. We don't really know if the set point is met. If the set point is less than contractual power, we don't really know. But the available power of the site was actually getting much lower. To estimate the available power between here, and actually this is the second spot where we tested the system here. We tried to get 16 megawatt, only got 5. At that time, then the available power, because we outside of the tolerance band, would be 5 megawatts, 735. So between here and here, the only way we could actually estimate this is to compute the available power. That's what we'll do in the next video. That's it for the operational availability. Thanks for tuning in. In the next video, we'll look at power availability. So even if we're not operating, the system will compute and estimate what the system is capable to do.